when I was in graduate school, I was having a casual conversation with one of my friends in the lab, and he mentioned that his father had died from ALS, amyotrophic lateral sclerosis. It's also called Lou Gehrig's disease. And I had to leave the room. Because at least it was my understanding at the time, there's a chance that he could end up with ALS just like his father. Maybe like 10% of the cases that were familial or hereditary in some way. And this was a long time ago before we had genetic screens and things like this. I think one of the most famous persons with ALS is Stephen Hawking. If you're a scientist, maybe he's one of the most famous. It's called Lou Gehrig's disease, but if you're not a history buff for baseball, you might not know who Lou Gehrig is. But it's a pretty devastating disease because your muscle control wastes away, but your mind is still fully functional. In most cases, mortality, you only last for a couple of years, a few years after the diagnosis. But Stephen Hawking was unusual. He lasted, I don't know how long, decades maybe, after the original diagnosis. And there's no drug for this. But I saw a news article that was talking about some pharmaceutical company that was developing a drug. Their developmental name was AMX0035. That's a typical, secret name that a drug company would give their molecule before it's ready for marketing. So let's go ahead and take a look at this drug, maybe the first drug for ALS. So this drug, AMX drug, is actually a mixture of two compounds. AMX0035 is they've taken two compounds and they've mixed them together. And what struck me, though, is that these molecules look incredibly simple. I realize that this one molecule right here does not look like a simple molecule, but it is a bile acid. You excrete this molecule out out of your digestive tract. So there's nothing strange about that. If you were into biochemistry, you might recognize this as cholic acid. Specifically, this is a cholic acid derivative. So taurine, it's another excretory molecule, has been chemically attached. It comes out in small amounts naturally, but they've synthetically attached these two so they could synthesize it on a large scale. And the other molecule that they're proposing as part of this this drug, this two-compound drug, is phenylbutyric acid. And that just does not look like a drug to me. It looks so simple. It's the kind of molecule we could teach you that you could figure out how to make using the tools we've learned in Chapter 16. And the thing that strikes me about this mixture of these two compounds is the dosing. I mean, you have to take grams of these things a day. That is not typical. That means if you had ALS, you'd be shoveling in spoonfuls of this stuff every day. And no modern drugs work like that. Modern drugs, they send synthetic organic chemists, like people like you, into the laboratory to design potent molecules, so you take 1 milligram a day, and that means very few side effects. There's going to be side effects when you're dosing up with anything at these high levels. But I think it goes to show that this is really, at this stage, maybe such a hopeless disease that people need hope. And it's better to have something that has side effects or where there's just crazy dosing than to have nothing at all. So I hope they get approval, hope somebody's working on better compounds. Just mechanistically, one of these is an inhibitor of Bax. So the mitochondria kind of holds mammalian cells hostage, and if you don't treat it right, it just commits suicide for the cell. It controls all these suicide pathways, and Bax is one of these suicide proteins. And I guess this terso molecule is a weak inhibitor of this suicide molecule, this suicide protein Bax. And phenylbutyric acid, turns out, has weak chaperone activities. So the endoplasmic reticulum is monitoring for the misfolding of proteins. And if there's misfolding, your cell's going to commit suicide. And so this helps use it in such high doses that it can help every protein in the cell, I guess, stop that misfolding type of event. So hope they send some chemists in to design something more potent. These dosing levels seem crazy to me. We are almost done with Chapter 16. here in our, sorry, we are almost done with chapter 16. So what did we talk about in our lecture on Friday? On Friday, we talked about all of these different, two different mechanisms for nucleophilic substitution, just insanely nucleophilic or basic conditions to do nucleophilic substitution. But the meat of this chapter, of chapter 16, is electrophilic aromatic substitution. Those 5 recipes, that rank order of substituents in determining how activated or deactivated a benzene ring is, and knowing which of those substituents are ortho-para-directors and which ones are meta-directors. You need to practice those tools on every kind of problem. And then I showed you, it's like, what happens if you use one of those 5 recipes and put on a group you don't want? Well, we have ways to change groups we don't want into groups we do want. You can hydrogenate nitro groups, like I'm showing you here. You can reduce carbonyl groups down to CH2 groups. And those are some of the ways that we can change groups we don't want into groups we do want. So I just wanted to wrap up chapter 16 by talking about the importance of practicing these reactions. So let's go ahead and take a look at a typical problem that you might face. One of the biggest challenges, I think, is when you're taking exams is to do multi-step synthesis problems, because oftentimes you have to know the reagents and have practiced them until you know them really well, and then know what order to apply those reagents. So let's take a look at this example. Suppose you were asked, how do I take benzene? And there's lots of problems in the back of the chapter that you should be practicing to practice with this type of stuff. How do you take benzene and convert it into some other complex molecule? Well, this is not complex, but it's one where you have to use a little bit of strategy. So you have to decide, do I want to put the nitro group on first, or do I want to put the carbon-carbon bond on first? And usually you don't know. Typically what you'll be doing is you'll try to draw out routes using both methods. Maybe I should make the carbon-carbon bond first. Maybe I should try both, and then see which one actually works. And the first one that works, that's the answer. Okay, but here's what you would have to do. The problem that you need to remember is the thing that you cannot do is you can't do Friedel-Crafts alkylation or acylation when there's a deactivator like a meta-director on the benzene ring. You can't put the nitro group on first, because then you can't do Friedel-Crafts acylation or alkylation. So you have to make the carbon-carbon bond first, and then you can put the nitro group on. And so let's go ahead and walk through some aspect of that. But let me just remind you, there is no simple way to put on a simple propyl group, because remember that, let me draw this the other orientation here. Remember that if you try to make a primary carbocation and then do Friedel-Crafts alkylations, they quickly do rearrangements. You would never get a propyl group attached to this benzene ring if you tried to do a Friedel-Crafts alkylation. You'd end up with hydride migration, and then it would be an isopropyl cation. So the only way that I gave you to put a primary alkyl group on the benzene ring is to do a Friedel-Crafts acylation first with a carbonyl group that you don't want. Here's a 3-carbon piece. Here's the acyl chloride, the acid chloride, and we use aluminum trichloride as our Lewis acid catalyst, aluminum trichloride. So the way we put on a primary alkyl chain is we put on an acyl chain, and we don't even want that acyl chain on there, but we know how to get rid of that carbonyl group. And so this would make a new carbon-carbon bond, right? You can't put a primary alkyl group, a linear alkyl chain, directly onto a benzene ring. And so now we don't want that carbonyl group. We've got to get rid of that. And I gave you 2 recipes for converting that double bond O into a CH2. And it doesn't matter which one. This substrate is not acid sensitive. It's not base sensitive. In this case, just to be different, I'm going to use the acidic conditions. It's called Clemmensen reduction. That's supposed to be a Z. I don't know if you can see that. I like to draw a bar through my Z's just so you know it's not a 2. It's like a science. I'm a scientist. Scientists put bars through their Z's. So we use zinc mercury amalgam, zinc parentheses, mercury, Hg. And you just have to remember that, right? You may not be that familiar with the elemental symbol for mercury, but you just got to remember Zn parentheses Hg. And this is under brutally acidic conditions, hydrochloric acid, and you typically boil this. in order to get those to work. So you can't have acid-sensitive functionality anywhere on your molecule and then use these Clemmensen reduction conditions. So this will convert that carbonyl group that you don't want into a CH2 group. So now we've got that propyl group on our ring. And so the rest of this is pretty easy. Now we just convert this into our nitro group compound. Now, we don't have a way to introduce compounds specifically to the para position. No matter what you do, you're going to get a mixture of ortho and para. But I will allow you in this class, if you get a mixture of ortho and para, to consider that to be efficient for either the ortho or the para. And I'm going to write down here plus ortho, just to make it clear that we know there's ortho in there. And typically on my exams, on my problem sets, I say, how would you efficiently convert the starting material on the left into the product on the right? And I ask you how to do it efficiently. And even though it's not efficient to generate a mixture of ortho and para, for these synthesis problems, I'll allow you to pretend that getting a mixture of ortho plus para is efficient. Okay, so that's it for chapter 16. 1 week from now, on Monday morning at 8 a.m., you're going to be in here taking an exam. That's our first exam, is chapter 16. This is the end of our exam 1 material. It's only one chapter, but we've covered a lot of material, and it's probably been a long time for some of you since you took organic chemistry. So it's not really a soft pitch to only cover one chapter, but this is your chance to really master the material and do well. So be in here at 7:55 a.m. in your seats, ready to take the exam, because we want to hand them out and start as soon as possible. And the next class starts, they want us out of here at 8:50, so we want to start on time. All right, that's the end of chapter 16, and let's move on to what to me just seems really exciting. And you may be thinking, aren't benzene rings exciting? Well, if I were honest about it, not that exciting. But what's exciting is chapter 17, because it is the start of adding to carbonyl groups. This is the way we make bonds to carbon. It's the way biology makes bonds to carbon. The making bonds to benzene rings is not as common. So let's go ahead and take a look at what's going on with this chapter 16. Now I want to start off by drawing out a carbonyl group. And let's just ponder on the structure of a carbonyl. So if I have a carbonyl group like this, I'll take a simple ketone. This is methyl ethyl ketone. What we're going to be doing in this class is adding to the carbonyl group, and I think it will help you to draw out a resonance structure of the carbonyl. And what I'm going to do when I draw this resonance structure, this is the best resonance structure. The best resonance structure always has the most bonds. The best resonance structure always has the most bonds. Why is that? Because you want to satisfy the octet rule. And the more bonds you draw, let me draw a resonance structure that's not quite as good, but is still important. It's just a different way to represent the same molecule. I'm going to take the electrons in that pi bond, and I'm going to give it to oxygen. We all know that oxygen is electronegative, wants electrons more than carbon, so this is the second best resonance structure. Now, it doesn't satisfy the octet rule. The carbon atom only has 6 electrons, so that can't be as good. But when we draw this other resonance structure, it is completely obvious which atom a nucleophile wants to add to. So if I had a nucleophile, if I gave you a nucleophile and I said, where are you going to add that nucleophile? It's totally obvious. You're going to add it to the carbon that only has 6 electrons, the C+. The carbonyl carbon is reactive not because it has a plus charge or a partial plus charge. It's reactive because it doesn't satisfy the octet rule. What we're typically not going to go through the trouble of drawing this resonance structure, even though I want you to keep it in mind, right? There's 2 resonance structures here, and this is kind of like a carbocation. If I were being more specific, I would say that's a carbenium ion resonance structure. They're the same molecule. I'm just representing this one molecule in 2 different ways. So we're typically going to be pushing arrows with the C double bond O resonance structure. Let me go ahead and draw out a kind of hypothetical nucleophile. I'll symbolize it with Nu, with a minus there just to emphasize that I think this is something very nucleophilic. And when we push the arrows, we're going to draw the arrows attacking the carbonyl carbon, like that, and then we're going to push the electrons onto the oxygen. And you're going to be doing this over and over and over again. You're going to be doing this in chapter 17. You're going to be doing this in chapter 18. You're going to be doing this in chapter 19. Guess what? We're going to be doing this in chapter 20. And in chapter 21, you're going to be doing this some more. And then in chapter 22, you're going to be doing this some more. If you take a standardized exam, you're going to be doing this. If you take an exam in another person's class at another university, you will be doing this over and over and over. So you have to get used to attacking carbonyl groups to make bonds to carbon. That's how we make bonds to carbon. Not through, let me show you what we're not going to be doing this quarter, and hopefully not much of this in the future. We're not going to be doing SN2. So you may be wondering, it's like, why did we spend 2/3 of this class talking about SN1 and SN2? I don't know why the books spent your time with that. Right? Remember this whole deal, it's like, when you try to do reactions with alkyl halides, especially things like secondary, you're suddenly thinking, well, am I going to make a carbocation first? Maybe this thing just pops out, and I'm going to do an SN1 reaction. And maybe I'm going to have carbocations. Or if I use a powerful nucleophile, I know it's going to attack something first, but maybe it's going to attack the proton and do elimination. And so you end up with these mixtures of SN2, and in this case E2, or if it's a weak nucleophile. We don't want that. That's why we do chemistry with carbonyl groups. So we don't have to worry about this SN2 and E2 and elimination stuff. What an awful nightmare. Let me go ahead and draw the product up above. This exciting product you get when you make a CC bond, because this is what we're going to be doing this quarter. We make bonds in this class in Chem 51C using addition to carbonyl groups. Let me circle that minus charge. Sometimes I circle my minus charges, right? Just because I want you to know that there's a minus charge, it's not a bond. Yep. Oh, yes, I do. Thank you for pointing that out. Everybody was wondering. Whoa, okay, back. There we go. Yeah, thanks for asking. Everybody would have been wondering about that. Okay, so we don't like SN2 and E2 because we don't have to, right? You always get those mixtures, just horrible. But making carbon-carbon bonds, or bonds to carbon by adding to carbonyls, that's what this chapter is really about, and that's what this course really is about. Okay, let me go ahead and, I apologize because just this morning I looked at the way I organized this slide and I flipped it upside down. So if you downloaded the notes before this morning, you'll find that the two examples are flipped upside down, but I just wanted to change that before today's lecture so it made more sense to me. So I'm going to talk about two different patterns of reactivity of carbonyl groups that will set up the theme for this whole course, for the bulk of this course, for all these chapters. We're going to talk about two types of reactions of carbonyl groups. We're going to talk about addition to C double bond O. That's a transformation called addition. And then we're going to talk about a transformation called substitution. And that's this course, really, is the bulk of this course is those two types of reactions, those two types of transformations of carbonyl groups. Now in chapter 17, I'm going to introduce this process called addition. And it's going to involve two steps pretty much every time. Sometimes there's extra stuff in there, but there's two key steps involved. So the first pattern of reactivities, we're going to take some kind of a nucleophile. So let me give you an example of a powerful nucleophile. Pretty much the only good nucleophile you've seen for forming carbon-carbon bonds so far is acetylide anions. You take alkynes and you deprotonate the H at the end, if it's a terminal alkyne, using sodium amide, and you make a powerful nucleophile for doing carbon-carbon bond forming reactions. They tried to tell you could use those for SN2, but you always end up getting mixtures of E2 and SN2. So here's where we really want to use these acetylide anions, is we want to use them for adding to carbonyl groups. That's where acetylide anions are useful. You can make billion-dollar drugs. They've done that using this reaction. And when we do that, we make a carbon-carbon bond. And I want to look pretty carefully at this intermediate that you generate. I'll draw the C atom in the middle, just to make it clear what's going on. And as I draw this out, you can see I've pushed the electrons up to the oxygen, and here's our amazing new carbon-carbon bond there. And when I look at this molecule, at this intermediate, what I note here is that none of these groups attached to that carbon I'll say no leaving groups. None of these are like a chloride or something that I might recognize as a leaving group. And that means this is stable. And it's just going to sit there. And we call this mechanistically, this step where you push electrons into a carbonyl and kick the electrons up to the oxygen atom. We refer to that mechanistically as an addition step. That kind of arrow pushing is called addition. Maybe that's kind of obvious, but it's very different from addition to alkenes, where the alkene was the nucleophile. And that's going to sit there. You could go to lunch and come back. It'll still be sitting there. You could take off for the day and go skiing and then come back the next day, and it'll still be sitting there. But, you know, as an organic chemist, I can't isolate charged compounds. Every single reaction we run in an organic chemistry laboratory, we convert things to neutral compounds, and we extract them into organic solvents, and then we evaporate the organic solvents. So if this isn't neutral, I can't deal with that, and no organic chemist can, I say, wants to deal with something that has charges on it. So let me draw the sodium plus. It's still floating around, but not important. So what we end up doing to these molecules is we do a second stage of the reaction called a workup. And in this case, that second step involves H2O. It's the, whoops, let me put it in black here. It's not really a mechanistic term. So we dump a bunch of water in there. I'm trying to draw this in black here. We dump a bunch of water in here. We just swamp it with water. I go to the faucet, I get some water, I dump it into my reaction. It's actually deionized water that comes out of our faucets. And I dump it in there. And the point of that water is just to stick a proton on that O-. A single water molecule is not more acidic than an alcohol OH, but I just swamp it with a bunch of water. And when I swamp it with a bunch of water, I end up with a neutral molecule that I can extract into organic solvents and then evaporate off the solvents, and I've got pure water. So, you know, this process that we have here is just protonation. Maybe I'll just call this workup. It's an aqueous workup, we call it. We're just getting the molecule ready to extract into our organic solvents. And the key thing is that this is a two-step procedure. And so you have to enumerate these steps. Step 1 is not the same as step 2. You cannot have water present in that first step. And so quite often we write numbers literally so you can see step 1 is you do one thing, and then later you come back sequentially and you do step 2. So this is a two-step process. It requires kind of like two chemical reactions. Now when we get to chapter 20, we're going to see a different type of substrate. And that different type of substrate is going to have a leaving group attached. Chloride, in theory bromide, but chloride is really the only common one. You're going to see things you don't even recognize as leaving groups. Alkoxy groups can act as leaving groups. We'll get to that a little more. But for now, just take it on faith that you can see that there's a leaving group attached here. And if we add a nucleophile to this, that nucleophile in chapter 20 is going to do the same thing that we're doing in chapter 17. It's going to add to the carbonyl group. If you add that acetylide anion, it would add to the carbonyl group. And this, we refer to this as addition. Mechanistically, that's called an addition step, and it's going to make a bond to carbon. But what we're going to teach you when you get to chapter 20 is that after you do that addition step, you're going to check and see if there's leaving groups on here. And I see a good one. Chloride's a great leaving group. Now, you might be looking for a nucleophile to push out that chloride. There's already a nucleophile right there. You don't have to have a separate nucleophile come in and do an SN2, because there is a nucleophile right here, that O-, that will push out. You can't stop this from happening. You can't stop that O-. It's going to push out that leaving group. And so we start off at the beginning of our reaction with a carbonyl, and at the end of the reaction, we have another carbonyl group. And you don't have any time to go to lunch, to go skiing. It's going to eliminate out the leaving group. And we refer to this mechanistically, this step, as elimination. This is an addition elimination. And it all happens in the same reaction. So notice there's a leaving group here, right? There's that leaving group. And this is what we're going to be doing in chapter 20. This is what we're going to be doing in chapter 22. We'll see this throughout the course, actually. So 2 types of transformations of carbonyls. This chapter is just addition stuff. Do you have a question? You know, there's 4 bonds to carbon, and we don't always draw the H's. So if I think the question is, do I need to draw that H there? Is that? I don't need to draw the H. Typically we don't draw the H's with skeletal structures. I'm trying to, I don't know why I drew that central carbon atom. I'm just so excited about adding to carbonyl groups. But generally, the rule is if you draw the C atom, you have to draw the H. If you draw an N, you have to draw the H. If you draw an O, you have to draw all the H's that are attached. But if you're doing skeletal structures, if you don't write the letter C, you don't have to draw the H's that are attached. So it's because I drew, the rule is because I drew this C atom right there, I now have to draw all the H's that are attached explicitly. And that's a great question because we don't, I'm not sure that we spend that much time covering that simple rule. It's like, once you draw the letter C, you've got to draw everything that's attached to the C, including the H's. All right, let's start off with our first amazing reagents that you have to know. You have to know in every organic chemistry class that's ever been taught. And our 2 amazing reagents are going to use H's as nucleophiles. You've never heard of H as a nucleophile before, I don't think. You've heard of protonation reactions where things attack H's, but I'm going to show you 2 reagents where H can be a nucleophile. And I'm going to start off with the best one, even though it might look a little bit freaky to you. So our first one, I'm going to use the word tetrahydridoaluminate or a hydridoaluminate species. The book calls this aluminum hydride, but I want to get that word 8 in there. Just this word 8 is so informative. Right? When I look at this word, this tells me, what does this word tell me? It tells me there's an aluminum atom, and it tells me there's a negative charge. Anything that ends in 8 has a negative charge. So I know there's going to be an aluminum atom with a negative charge there. Let me put it in black. And then over here, I've got hydridoborate. Right? There's a boron, and there's an 8. So over here, there's going to be a boron atom, and that boron is going to have a negative charge. And that tells me the fact that it is a negative charge, the fact that it is an 8 complex, tells me that every bond to that atom is nucleophilic. Wow, just from the name, I know every bond to that atom is nucleophilic. Let me go ahead and draw out the bonds for these 2 reagents here. So the tetrahydridoaluminate, actually let me draw the hydridoborate species. So hydridoborate has 4 bonds, and they're bonds to H's, and I think you're going to be using this reagent in the 51LC laboratory, tetrahydridoborate. There it is. Boy, look at that. Those bonds to the H's are nucleophilic. The BH bonds are nucleophilic. But it's not the boron atom that's nucleophilic. It's the H's that are nucleophilic. Those H's are going to leap onto carbonyl groups and form H carbon bonds, hydrogen carbon bonds. Now let me go ahead and draw out the tetrahydridoaluminate species, the hydridoaluminate. And I'm going to do something that really exaggerates this structure, because if I don't exaggerate it, you won't remember. I'm just going to draw these bonds freakishly long. You know, aluminum is in the same column as boron, but there is a big difference in the reactivity. There we go. See, if I didn't draw it long like that, you wouldn't remember it. Long bonds are more reactive than short bonds. When you drop down to this 3rd row of the periodic table, boron's in the 2nd row. But you drop down to the 3rd row, those bonds are long, and they are nucleophilic, and they are basic. Tetrahydridoaluminate, because of those longer bonds, is way, way, way more reactive. Way more reactive because of those longer bonds. And if I write it out as like this, if I write it out the way they do in the book, you don't really get a sense that lithium aluminum hydride is more reactive than sodium borohydride. Those are the common salt forms. We get these as powders. They look kind of similar. What's the difference? So I'm going to draw those with bonds that are 1,000 times longer because I want you to remember that. Yeah?
What characterizes the H's to have to be nucleophilic?
Because there's a negative charge. Because there's this negative charge on this aluminum atom, those bonds are nucleophilic. And if I took another molecule like alane, I don't have a lot of room to draw the long bonds here. With no negative charge, so aluminum normally has only 3 bonds. That's not nucleophilic at all. In fact, aluminum in that case is a powerful, powerful electrophile. So that negative charge tells you that those bonds are nucleophilic. And it's the bond length that tells you those bonds are powerfully nucleophilic in this case. Okay, so I got 2 reagents. One is way more reactive. That's the aluminum one. Sodium borohydride is still pretty useful. It's actually reacts quite quickly with carbonyl groups. Let's go ahead and watch how these things are used, but I want to give you a cautionary note. We're going to start off with the one that's really reactive, and I want to give you a cautionary note about what kinds of conditions you use when you use this. They call it lithium aluminum hydride is the reagent. That's the powder that you buy. It comes in a can, in a bag, or you can buy solutions of it. The problem with lithium aluminum hydride is it reacts instantly with water and alcohols. So if you untie the bag to go weigh out some of this powder in the balance, as soon as you open that bag up, you're thinking, oh my gosh, the air is wet. It's starting to destroy the reagent in the bag, so you try to close the bag really quickly. But especially in solution. If I add lithium aluminum hydride, this tetrahydridoaluminate species, to a carbonyl group, right, it's great for forming CH bonds. See this new CH bond that we generate over here? Look at that. So it's the hydrogen atom that forms the bond to the carbonyl carbon, not the aluminum. I realize the aluminum has the negative charge, but you have to stop forming bonds with charges. Charges don't form bonds. Electrons form bonds. It's the H that is the nucleophile, not the aluminum, right? You want to get the negative charge off the aluminum, and the way to do that is you rip away a hydrogen atom with the electrons. You take those electrons away from aluminum, and then the aluminum can become trivalent and neutral again. Now, the problem is that if you try to do a reaction like this, so I'm showing you right here what happens if you exclude water. But what would happen if I did this same reaction, if I put that same ketone, acetone in with lithium aluminum hydride, with tetrahydridoaluminate species? So what would happen if I had some sort of an alcohol in my system, in my reaction flask, or a water molecule? That tetrahydridoaluminate species will go searching around. It will know that you had a water molecule somewhere in your flask. And that tetrahydridoaluminate species will say, oh, should I attack the carbonyl? Oh, no, wait, there's an OH bond in there. I'm going to deprotonate that. And you can't stop that from happening. The OH will always deprotonate faster than you add to the carbonyl. And this is one of the challenges with lithium tetrahydridoaluminate. With lithium aluminum hydride, it will act as a base faster than it acts as a nucleophile. And so instead of getting bonds to carbonyl groups, instead of adding H's to carbonyl groups, you're simply going to deprotonate your alcohol or your water, and there's easier ways to deprotonate alcohol and water. The problem with this is it is so aggressive that the hydrogen gas that you generate by forming a bond between 2 H's will catch fire. It generates so much heat that the hydrogen will ignite, and then you're going to have a big fire on your hands. So we don't run reactions with lithium aluminum hydride in the presence of water. And you might be saying, well, why would I ever think? I'll show you why you're going to do this. You're saying, of course, that's so obvious, Dave. I would never do that. Yes, you're going to do that. You're going to make a mistake. I'll show you in a little bit the mistake you're going to make. It's going to cause you to set up propose reaction conditions that are going to cause fires. So this is way faster. If you have OHs, you're just going to deprotonate faster. So the book, I think, kind of skips around this, or I think it tries to imply that you could use lithium aluminum hydride for SN2. You're not going to be using lithium aluminum hydride for SN2 reactions, no matter what the book says. No chemist would ever do that. It doesn't work well. You have the same problems with E2 eliminations or just sluggish reactivity. Lithium aluminum hydride is for adding to carbonyls. All right, so let's go ahead and take a look at the way we're going to depict this. So if I give you this reaction, here's an example. What's happening in this transformation? I hope we can all see what's happening in this transformation. What's happening in this transformation is we've formed a CH bond. And it's going to be hard for you to recognize that that's the number one thing that happened because we don't draw the H's. You may be thinking the number one thing that happened is we broke the CO double bond. That's not the number one thing that happened. What I expect everyone in here to see is that you formed a new bond to H. And if you can't see that right off, then you go practice seeing the H's. Go get some practice being able to see every H, even if it's not drawn for you. So this is where we use these reagents. You could use the sodium borohydride reagent or the lithium aluminum hydride. I'm going to show this with our lithium aluminum hydride reagent. And the way I would do that is I would write lithium aluminum hydride. But what I would not do is I would not simply write the word water under there. Because if I put water with lithium aluminum hydride and write it in this way, that implies that I'm mixing together lithium aluminum hydride and water. And I already told you what would happen if you had water in your reaction mixture. You're simply going to react the lithium aluminum hydride with the water, and it won't touch that carbonyl group. We have to somehow show people that the way we ran this reaction is the first thing we did is we dumped in the lithium aluminum hydride. And the way we do that is we enumerate the steps. I'm going to do it the way the book does it. They put brackets with Arabic numerals in there. But it's also common to enumerate the steps using Arabic numerals in half parentheses or Roman numerals with half parentheses. Just something to indicate that you didn't dump everything in there at the same time. So you first dump in the lithium aluminum hydride and you let it react until it's done reacting. And then once all the H's are done adding to all the carbonyls, this could be later in the day, after lunch, in the evening, you come back and you dump a bunch of water in there. And at no point in time did you ever have lithium aluminum hydride swimming around with water. Right? It's only at the end of the reaction do you add water. And you have to enumerate it like this. So if instead you choose to do it like this, you wouldn't choose it, you would just forget. If you forget to write that enumeration, if you just write it like this, I'm just going to tell you right now, that's totally wrong. I will give you no credit for that. Totally wrong. 0 points. It's so important to not set up reactions that catch on fire or that wouldn't work at all. Not only would it not work, it would also be dangerous. You don't get any points for that. And you might say, I had the reagents right, I just forgot the numbers. Well, if you forgot the numbers, then you didn't understand what was going on. So you have to remember this, and this is true in every organic chemistry course. This enumeration is important. Okay, let me step back, though, and talk about this sodium borohydride, because it is weak. I told you that lithium aluminum hydride reacts with, let me do a different substrate here just to have more examples. So I told you that lithium aluminum hydride reacts quickly with water and OH compounds, but sodium borohydride is not as reactive as lithium aluminum hydride. And you could never in a million years have known this. Here's what you couldn't have known. What you couldn't have known is this sodium borohydride reagent is so choosy and so selective that it will react with carbonyls even in the presence of water. Now, we don't run sodium borohydride reactions in water because organic molecules are not soluble in water. So we use methanol, right? Organic molecules dissolve in methanol. You can't use water. Your organic compounds would be floating at the top of your aqueous mixture. So sodium borohydride is amazing because you can have the alcohol, in theory you could have water, except for that solubility issue, right there in the reaction mixture, and you don't need to enumerate the steps 1 and 2. Would it be wrong if you enumerated the steps? Well, you have to have a solvent for the reaction. And sodium borohydride, in all the cases that I've ever seen, you do it in methanol. And it's possible that in the lab they use ethanol because it's not toxic. People drink ethanol. But that's not typical. We usually use methanol because it's just easier to evaporate. Let me draw those H's on here. I just formed a second CH bond. So let me draw those. Normally I don't draw the CH bonds, but just to help get you into this, see, we formed a second CH bond with that. And we don't need to enumerate the steps here. Don't enumerate the steps. Just write sodium borohydride and methanol. Again, the lab uses ethanol just for toxicity reasons, but in every organic laboratory, normally you use methanol as the easy-to-evaporate solvent, much easier to evaporate than ethanol. Now, let me just mention here, I think I already mentioned this before, that the reagent combinations that we use, why don't we use sodium aluminum hydride? It just turns out it's not soluble in anything. And you don't need to know that, but if you're wondering why is it sodium borohydride and not sodium aluminum hydride, it just turns out that sodium aluminum hydride is not soluble. And why don't we use lithium borohydride? Because it's more expensive. So if you wrote lithium borohydride, I'd count it right, but I'd say, geez, no, I've never heard of anybody using that. So it may seem strange to you that we have these two particular lithium and sodium counterions. Yeah, you have a question back there.
Yeah, so basically the difference in reactivity is due to the difference in atom sizes.
Yeah. Yes, the aluminum H bonds are longer, right? There's not, and that correlates with electronegativity in some way, but it's the long bonds. Longer bonds are more reactive. Carbon-iodine bonds, more reactive. It's easier to do SN2 on carbon-iodine bonds. Their iodine bonds practically half broken the whole time, because the bonds are long. Longer bonds are easier to break. Longer bonds are more nucleophilic. I mean, that is a hard rule. That's a hardwired rule. All right. Now, we have to think about stereochemistry. At the front page of my exams, if you look at my exams, it says, clearly indicate stereochemistry, if any, unless I specifically say, don't worry about stereochemistry. If you generate new stereogenic centers, you're going to generate a mixture of stereoisomers, and you have to indicate the presence of both of those. So I'm showing you up here a typical reaction where you would add to a carbonyl. You're doing a lithium aluminum hydride reduction. Notice how we've done 2 steps. Sometimes I write the word workup, but as we go through the course, I'm going to stop writing the word workup. But for now, I just want you to know, I'm not trying to use the water as a nucleophile in an SN2 reaction or an SN1 reaction. I'm just trying to protonate something so I can get neutral molecules to extract into organic solvents. You don't have to write the word workup. The book doesn't write the word workup. I just want you to know I'm not doing SN2 with the water or SN1 with the water. Okay, but notice here in this reaction, what you should have been observant about is the fact that we are forming a bond to an H atom, and we've generated a new stereogenic center. And that means we're going to end up with an equal mixture of both enantiomers. So I expect you to tell me that both enantiomers are present. You can either draw both enantiomers, or you can simply, in my class, allow you to write +E. To indicate that there is a mirror image molecule. You can't do that with diastereomers. I don't allow that because then there's like 3 different diastereomers and you can't write +D and be unambiguous about that. So in reactions that generate stereogenic centers, I expect you to show the stereochemistry using dash wedge notation and clearly indicate the presence of that stereoisomer. Now let's go and walk through this. The important point about this is that there are 2 faces to the carbonyl. There's a top face and a bottom face. And a hydrido group can add from either of those faces. So if I have this hydrido aluminate species right here, look at that bond. It's so nucleophilic. It's the H atom that's nucleophilic, and it's going to add, and you have no control. It's just these 2 things colliding with each other. Hundreds of thousands of millions of times they're colliding. And every once in a while they will collide with enough energy and with the right orientation to form a bond. Here we go, here comes the bond. Boom, there we go. New bond between H and C. And half the time it's going to add from the top face, half the time it's going to add from the bottom face. You've got 6.02 times 10 to the 23rd molecules in there. Half of them are going to be, I'll use wedge for this carbon-carbon bond here. There's my new H, if it adds from the top. Now there's a lot of different dash wedge notations I could use. Like I could put the oxygen atom with a dash line, or the phenyl with, I'm just trying to show you that the H added from the top, so that's why I'm choosing to draw the H wedged. But there's not a single representation for this enantiomer. And if you're wondering whether your molecule matches mine, then assign R and S Con-Ingold Pralog configuration and see if yours is R and mine is R, if you really want to match up any 2 representations. Okay, you can also add the H from the bottom face, right? The hydrido group can also add from the bottom face of that molecule. And this time I'll wedge the ethyl group. And you get an equal mixture of these. You have no control over that. 6.02 times 10 to the 23rd product molecules. Half of them have the H added from the top. Half of them have the H added from the bottom. The bottom one is they're clearly enantiomers of each other. I'm just trying to show you the impact of adding from top or bottom face. And then this just sits there, and later you come back and you do an H2O workup. So I'm just going to choose one of these molecules. I'll choose this top one just to do the arrow pushing, and then we protonate, and that generates the product of this reaction, which has this new, I'm not going to draw the H this time on the, there we go. And if you drew one of the other bonds as a dash or a wedge, and you want to check whether it's the same way that I depicted it, then assign R and S, and then you can. Now I have to indicate that that other enantiomer is still there. So normally with arrow pushing mechanisms, you don't have to keep track of enantiomers. Usually I ask you to keep track of enantiomers and write plus E if I draw a box and I say draw the product in the box. That's when you need to write plus E. But for arrow pushing, we don't keep track of enantiomers. Because this slide is about stereochemistry, I'm keeping track of enantiomers during the arrow pushing, and that's not typical. Okay, the book has another section. There's a very special, it's not a super unique or special, they just chose one arbitrarily. There are a whole set of reagents that allow you to deliver a hydrido group from one face and not the other. Like alcohol dehydrogenase that you have in your body that reacts back and forth, oxidizes and reduces alcohols like ethanol, adds to one face of the carbonyl group, top versus bottom. And there's chemical reagents we have, chiral chemical reagents. One is called the CBS reagent. That's the abbreviations for the inventors. I'm not going to put that on my exams because there's no reason for you to memorize this one reagent always gives you the R configuration or always adds from the top face. I don't think that's a valuable skill for you at this stage to memorize that one particular reagent because we have thousands of these reagents. Okay, so when we come back on Wednesday, we're going to keep adding things to carbonyl groups. Over and over and over again, we're going to be adding things to carbonyl groups. We're even going to do some substitution in this chapter, even though most of that's in chapter 20. So I realize in discussion section we're working on chapter 16, but you need to be starting to think about working problems in chapter 17. There's this relentless pace for the class. Keep on working problems in the back of the chapter. It's great practice.